Hello everyone, I'm Vivek. I'll be discussing the response time scaling of gas sensors, and so this is a numerical study, and we'll get some insight into what is known prior uh, about the response time scaling versus the target gas concentration. Uh, So let's start with a very basic system overview of any gas sensing. So we expect an active area of the sensor, and there is some target gas concentration in the ambient. There will be processes like reaction and diffusion of, near the sensor area. And to calculate the response time of any such systems, we need an idea of which of these processes is the limiting process in the detection. How does the sensor geometry affects these processes, the diffusion dimensionality and all, and what is the detection threshold, what is the minimum amount of adsorption or reaction you require on this surface for a measurable response. So these kinds of the idea of these things helps us to calculate the response time of such sensors. So what is known to us, so let's look into the diffusion limited sensing. So here we have uh, a sample graph of the integrated density of the gas on the sensor surface and how it varies with time. So this is the flux that has been integrated over the sensor surface, and what we know is that depending upon the geometry of the sensor, whether it's a 1D diffusion case or a 2D and 3D diffusion case, the transient response, the transient integration of the particles on the sensor surface follows a different law with time. And once it's the steady state, the flux becomes constant. Then for all sensors, you expect the same response, that is t to the power 1. So if it is a diffusion limited sensing and your threshold lies somewhere here where uh, the detection happens in the transient case, then for different sensor geometries we know that the dependence on the ambient concentration follows different laws. So because the integration is fast in a higher dimensional sensor geometry, the response time uh, the response time scales slowly. For lower concentrations also, the response time for detection is lower for the higher geometry, and for 1D case the response time scales much faster for lower concentrations. So this is true for like the diffusion limited detection and in the transient region if your threshold falls. But the important feature which I want you to take away with is that this scaling is uniform for all concentrations here. So it's following a regular scaling law throughout the different C naughts, the ambient concentration. And so what motivated this numerical study was one observation of ozone sensing on perovskite sensors. So this was one experimental study, and here we are seeing that there is some sensor response for different concentrations of the ambient ozone, and they identified two regions with respect to the response time. So there is a region above 180 ppbs where there is a sharp rise in the response, and uh, then for even lower concentrations this sharp rise is replaced by a very slowly rising curve here. So there is an abrupt increase, or there is an abrupt change in the scaling law with the concentration. And so we wanted to study what might be the reason for this specific case of ozone. So the model which we have used here is a simple 1D diffusion model, and so the chamber is such that it is selective to ozone. That means that it is confined enough that there is a possibility that ozone in the ambient versus ozone in the confined space can have different uh, stabilities. So there are some gases which remain stable on their own, and so there are some gases which require a dynamic equilibrium to maintain their concentration. So ozone is an unstable gas; it maintains its concentration in with respect to a dynamic equilibrium, there are many processes happening outside the chamber. But once it enters the confined space of the chamber, there's a possibility that the ozone decays with time. So the depending upon the temperature and moisture levels, the decay time of ozone varies as a couple of minutes. So, and this is very close to the response times reported in experiments. So there is a so there will be a competition between the decay. There will be an inclusion of decay as well along with the diffusion happening inside the sensor chamber. So the numerical study has these three important conditions. It's a 1D diffusion. The boundaries are Dirichlet, the fixed ambient concentration here. And since it's a diffusion limited case, we assume that the reaction is fast and there is no concentration here. It quickly goes to zero. Everything gets absorbed when it's on the surface. And within the sensor chamber, there is a lifetime of ozone, and we assume an exponential decay case. So we modify the Fick's law for, so this is without the decay, and this is what we expect for the 1D diffusion. This is well known for a stable gas. Now if we assume the sensor model that we uh, proposed, so this is the situation. In the Fick's law, we get a decay term, exponential decay with some lifetime. So uh, so we have chosen a lifetime of about 3 minutes, and what we want to compare in this sensor model is that with respect to a stable gas, there is a fall of the concentration ceiling because of the decay, which has an impact on the flux reaching the sensor surface. So this affects the integrated density with time. The exponent which we saw earlier in the case of decay changes. So these are the graphs which are calculated for different concentrations, ambient concentrations, and what we see here is that the t to the power half case which we see is the one which is shown in uh, yeah. So actually this legend is wrong. The dotted thing is one which continues for the tau d equal to infinity case when there is no decay. The t to the power half law continues. But in the case of the decay, when the time scale reaches that of the lifetime of the decay, then the concentration which gets integrated on the surface does not continue on the same path. There is a marked deviation here. And in fact, this deviation, we expect it to be dependent on the value of the lifetime itself. So here we have done the simulations for different values of tau d, the lifetime, and we see that compared to the infinity case, the exponent is a sharp function of the lifetime. So the lifetimes are varying linearly, and the exponent is also varying linearly. So there is sharp sensitivity to the lifetime itself. And so if your threshold is such that for some concentrations it intersects the integrated density in the phase where uh, the t to the power half law is being followed versus other concentrations in which it intersects, where it intersects this integrated density curves where the decay has kicked in, the effect of decay has kicked in, there we can expect that the scaling law will change dramatically. uh, so these are the two expectations which we carry forward, that there'll be a change in the response time scaling with c naught, and that will also depend on the tau d. So this is the response time scaling for 1 decade of C naught, in which the C threshold does satisfy that criterion that for some concentrations it lies in the region of t to the power half, and for even smaller concentrations the effect of the decay is evident. So here we are seeing the two effects, the two expectations. One is that this is the uniform scaling law which is known from prior literature, but in the decay case, the scaling law for higher concentrations is the same as what is known previously, but it changes for lower concentrations. And uh, this change, the change in the slope, is a function of tau d for smaller decay constants, and for the same concentrations we see a much more higher response time. And what interesting feature we directly derive from this curve is that where we get this knee in the curve, that is where we see the change in the scaling law, that is very highly correlated. The response time at that knee is very highly correlated to the tau d itself. So if there is an unknown gas whose decay constant is not known, we can perform a response time versus ambient concentration over that gas, and the scaling law change will help us determine what is in fact the decay constant or the lifetime of that particular gas. So to conclude, the main takeaways of this work is that we need to take into account the spontaneous decay of gas when it is in the confines of a chamber. And for diffusion limited detection, we can expect that the response time will scale differently for large concentrations, and with a different exponent for small concentrations. And going forward, this can be important information for chamber designers, for flow designers, because this is expected to be at operation at all geometries, at 2D, at 3D itself also. And this tau d, the lifetime, is a strong function of moisture and temperature. So we would like to keep this a check on lifetime by keeping a check on the temperature and moisture inside our chamber to avoid the decay of the gas. And yeah, so this I already discussed. The decay lifetime characterization can be done by doing a response time versus ambient concentration study, and the knee position is correlated to the decay constant of the gas itself. Uh, Thank you for listening. Discuss any questions.